Hi, everyone. This is the first lecture on content in Real Analysis 1. What I would like for us to do is first work through the basic concepts of what a set is, because we will actually need to use the concept of a set in order to define our axiomatic structure for the real numbers. So this lecture, we will look at sets. The next lecture, we will look at R, the number line, the assumptions that we will place on that, and then we're going to really get going. So this is like the first of two somewhat preliminary lectures. So I've put up here the basic idea of what a set is, but I want to emphasize that we are going to be talking about subsets of real numbers. So some of this discussion is broader than we need it to be. What we say is that a set is a collection of objects called elements. We typically use this capital letter notation to denote sets, and we often use little letters to denote elements. If I wanted to say that an element X was in the set A, for example, the real number 3 is in some set of real numbers, we would write X is an element of A. That's it. So that's what this notation here means. If you see that and you haven't seen it before, that's the belongs to symbol. If, on the other hand, X is not an element of A, there are two ways you might express that. You could just say, hey, this is not the case. Or, and I'm going to bring in a definition here, if X does not belong to A, X belongs to the complement of A. So this is X is not an element of A, which is equivalent to saying X belongs to the complement of A. So that's everything which is not in A. So we'll actually talk more about that in a little bit. So let me move on to this. Again, we're going to be talking primarily about subsets of real numbers. Later, we might talk about sets of functions or something like that, but our sets are not going to be too exotic, assuming that you're coming into this course with a thorough treatment of calculus. If you want to describe a set, there are typically two ways that you might do it. You might just say what the elements are. So that could look like the set A consists of the numbers pi, e, and 1. This would be a finite set whose cardinality is 3 because it contains 3 elements. You could also provide the set not using this curly bracket notation. So this here is like the box that I put the numbers in. You could say A is all of the real numbers between 0 and 1 inclusive. So this is like a description of all of the elements in the set A. We could say A is the set of positive even numbers. Sometimes, if it's clear what the pattern is, you can just say what the first few are and then tell the reader that what you're observing here will continue in a natural way. So next you would expect me to write 10, 12, 14, etc. All right, so those are some ways to express what a set is. Often we might have an algebraic description for what it means to say an element belongs to a set. I just take this set of even positive integers that I just wrote down. What you might say is, this is going to start using notation here, and I'll try to talk through what I'm writing down symbolically in case some of these symbols are unfamiliar. I'm not going to necessarily write out a definition for each symbol that I use, but I think that you'll pick it up as we go through them. So I'm going to say A is the set of elements which are real numbers. So here X is an element of the set of real numbers such that, so this colon here is telling me I'm about to tell you what X has to satisfy to belong to A. X equals 2J, where J is what's called a natural number. That. And what I've just written down, I'm going to grab a new color. Oh, here we go. Is a algebraic description of even positive numbers. I'm going to define this symbol natural numbers in a bit. Actually, I'll take you through sort of the most famous subsets of the real number line. But basically, you think of these as your counting numbers. For me, that starts with 1. 1, 2, 3, 4, 5. So I'm saying that the set A consists of the elements which are real numbers, which can be expressed as twice a counting number. So 2 times 1, 2 times 2, 2 times 3, 2 times 4, that's going to return us this set. And that's really all I wanted to say about how you write down a set. I typically use this colon symbol to mean such that, but you might see a vertical bar there instead. It's the same thing. So you could say X is a real number vertical bar such that x can be written as twice j, where j is one of the natural numbers. Okay, I'm going to step aside just for a moment and then we will look at a quick paradox. I don't want to get off topic because, again, we are focused on real numbers and subsets of real numbers. I just want to mention a paradox that you might encounter if you're learning about sets for the first time before we come back and talk more about these famous collections of sets. As I was putting together this lecture, I had a little debate with myself about whether or not this example was a good idea to include in this video, and I decided to do it because I think it's a fun thought experiment. So let me just give you this object R, which is being presented as a set, but whether or not it's actually a set is something that we will discuss in a moment. So for now, let's just treat it as a collection of objects. So this collection R consists of elements, name them little x if you'd like to, elements x with the property that these elements are not elements of themselves. Take a moment to just turn that idea around in your mind for a moment. And once you feel like you feel comfortable with this notation, answer this question as best you can. So, is it fair to say that R is an element of itself? I'm not actually going to take you through the thought process behind the answer because I think that you probably got there yourself. And I don't want to spoil that. So reach the conclusion on your own. I will tell you that the answer to this question is both yes and no. So actually, there's a huge contradiction here, and hopefully, you see why that must be the case. So if you were trying to make one of the conclusions work, you won't be able to. This is a paradox called Russell's paradox after Bertrand Russell. And it's just illustrating the idea that to say a set is just any kind of collection is not quite right. So there's a little bit more to, say, logic and set theory than this sort of naive construction of just have a box with elements inside of it. I don't want us to get off track into a discussion of, say, axiomatic set theory because in this class, we are just going to be talking about subsets of the real number line. So we are not going to have any paradoxes arise when we look at sets of real numbers. In a moment, let's actually meet some of the famous sets of real numbers. I will go through famous notation for these sets, and we will talk about these sets like almost every single lesson. So do make sure that you leave this lecture comfortable with the famous sets of real numbers. So I would say that these are the most famous subsets of the real number line. In fact, I have the real numbers themselves on this list. I've ordered this, though, to match kind of like what I think people learn about as children. So, when you first learn about numbers, you probably started with your fingers, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Those are natural numbers. For me, throughout our discussion of real analysis, natural numbers start with 1. So I will think of these as counting numbers that you literally can count on your fingers. However, in some discussions, other textbooks, etc., natural numbers may include 0, and that is also a valid construction of the natural numbers. There's no right or wrong answer for whether or not 0 needs to be a natural number. I think natural numbers really should start with 1. 0 is something a little bit more exotic to me than a counting number. Okay, so anytime I write down n, I am not including 0. It's often the case that we might have a component that looks like 1 over n, where n is a natural number. So that's also a practical consideration because you don't want to have to write down 1 over n, where n is a natural number, but not 0. So I think it's a little bit more convenient to leave 0 out of this list. Okay, so that's probably like what you thought numbers were when you were little. And then you may have learned about negative numbers. So this is like going to the left and to the right. Why can I not write that? -3, -2. Integers, right? Okay, and that includes 0, obviously. So natural numbers, integers, every time I write down the bold face N and Z, I'm not going to spell out what that means. For the rest of our study together, we know what natural numbers and integers are. Rational numbers are fractions of integers. So like 3/5, -7, which you could think of as -7 over 1, 22 over 11. Okay, that's just 2, but that's also a rational number. Okay, so here's how I like to write this. This is the set of numbers of the form P over Q, where P and Q are integers, but obviously I don't want to divide by 0. So I like to say that P is any kind of integer but Q is a natural number. And you can take a moment if you need to verify that that will capture all rational numbers. I also want to make a point here. Why do we call them rational? The word rational contains the word ratio. So these are numbers which are ratios of integers. The next set is more sophisticated if you think about it. So natural numbers, I mean, these are numbers that you can kind of get to with your fingers, and then we pick up the idea of zero and negation to get integers, and then we can build rational numbers. So all of these feel like ideas that you could have developed at a young age. The real number line itself contains numbers like pi, square root of 2, etc. So I'm not going to write down a description for it because this is our big set. This is what we are building subsets out of. So we will just take the real numbers for now in this lesson as basically just this kind of number line, but we will be kind of filling in this number line over the next several lectures. So I do want to dig into the structure of R, but that's coming up. So there's a lot going on here that I can't just write down quite as easily as we did in the 3 examples above. When describing the number line just now, I mentioned pi, did I mention e? I can't remember, square root of 2, numbers that whether or not you can prove it right now, you might think can't be written as ratios of integers. So those are numbers which take a different form. At the moment, can I prove for you right now that pi cannot be written as a ratio of one integer to the other? To say that there is no such representation is actually quite difficult in this moment. So we will talk more about R, and we will talk more about the set of irrational numbers. And I'm not going to write down a description for this because all I'm going to say is that the set of irrational numbers are the numbers which can't be written as rational numbers. So in fact, let me say that this is R, take away the set of rationals. So this is like set minus. So it's saying everything which is a real number but which is not rational. Or I'm just going to rewrite what I have over there. It's the complement of the rational numbers. You might not necessarily even be convinced that there is such a number. So maybe this is the empty set, which I didn't put on this list, but of course the empty set contains no elements. More discussion about these two sets is coming up. So we're going to talk about the structure of R. We're going to verify that, yes, irrational numbers exist. And in fact, there are many more of them than there are rational numbers. All that is coming up. I get really excited about these topics, so I have to stop myself from going further. What I would like to do for the rest of this video is talk about how to show that two sets are equal. So to do a set equality proof is a proof technique. We will have just some nice examples of that to finish this lesson. Now I would like to talk through what it means to say that one set is a subset of another. This idea is called set containment. And in a few minutes, we will establish set equality. We say that a set A is a subset of another set B if every element in A can be found in B. So you can think of A as kind of sitting inside of B. I am going to show how this definition can be used to prove statements like this exercise right here. But before we do that, let me talk through this definition. And in particular, I want to establish a notational convention that I use, which might look a little bit different than your textbook. So I have here just this kind of plain subset symbol. For me, that is non-strict containment. Let me distinguish between strict or proper containment and not strict. So not strict or not proper, I'll say not strict, non-strict, that's what I'm going to say. Basically just general containment. Is the definition that we have here. All this is telling us is that everything that you can find in A, you can also find in B. A is a subset of B, means if X is in A, then X is in B. What I want to point out here is this symbol that I use. I'm not the only person to indicate this idea of just subset containment, just general containment using this symbol, but You may see more commonly in books the symbol subset or equal to. So this indicates that A could be a subset of B, which feels sort of smaller. Smaller can be a dangerous word to use here with sets, but the idea is that, A lives inside of B, but maybe there's more to B than just A. So that's like a kind of proper containment. Or it could happen that A and B are actually the same set. This statement would be true. So this is like subset or equal to versus strict containment or proper containment. Let me say A. Here's what I would write, and you might never see me write this because it just doesn't come up very often. But if I wanted to indicate strict containment, here's how I will do that. So this is like A is a subset of B, but it's not equal to B. And we haven't defined set equality yet, but let me just give you a working idea of this expression. If X is in A, then X is in B. In other words, A is a subset of B. But there exists a Y in B, which is not in A. So here, with this idea of strict containment or proper containment, the idea is that A isn't accounting for all of B. So there's something in B that doesn't live in A. And here, you might see in books that this idea should be expressed with just this symbol. I really am not the only person that just uses this to mean general subset. We are almost always working with this idea of containment. And this symbol, it's just easier for me to write. I like it better than this. So I will almost always write this, and I just mean general containment. I'm not trying to emphasize proper containment. It's perfectly fair for me to say, for example, that A is a subset of itself like this. Okay. So A is a subset of itself, but A is not a proper subset of itself. For me, this notation is okay. All right. And again, I can't really think of any situation where I'm going to need to insist on proper containment, but if I do, I will highlight that. I will use a symbol like this, and I will stop and talk about it. So anytime I write subset or talk about set containment, I just mean this and pretty much only this. If X is in A, X is in B, and that's the only implication that I'm trying to establish with this notation. Okay, there was one more thing I wanted to say before we jump into this exercise. And that is that we can go ahead and write down a pretty famous chain of subset containments using the sets that we already saw. So we started with natural numbers, probably the first numbers that you learned as a child, unless your childhood was strange. So you're counting numbers. They are positive integers, which means that they are a subset of all integers. Integers, or whole numbers, can be written as ratios if you just set the denominator to be 1. So every integer is, of course, a rational number. And then the question is, rational numbers are a subset of real numbers. Is there anything else? The answer is yes, but this chain of implications is pretty immediate from our definition of these families of numbers. So all natural numbers are integers, all integers are rational, all rational numbers are real numbers. We have to talk about irrational numbers in a little bit more depth, but that's going to be a separate line. You could say this. I'm being a little bit weird here, but I'm just trying to say, until you study them, it might not even seem clear that there are irrational numbers, but there are. I'm going to talk about like nothing but irrational numbers for a whole lecture in just a few videos or so. Okay, the heart of this statement is really just to establish that this symbol means this definition for me. Let me step aside, erase all of this, and then we will work through this exercise and just a couple others. These are pretty fast proofs, but it's important that you understand the mechanics of how to prove this kind of statement. Here's what we want to show with this statement. Given that the set A is a subset of B, we want to prove that B complement is a subset of A complement. With set proofs like this, where you're showing set containment, Generally, do not try to work with the entire set all at once. What you want to do is think about how the definition is phrased here. It's in terms of elements. So go down to the level of elements. Let me write, want to show if X is in B complement, then X is in A complement. That is the definition of set containment. If I can show that, take any X which is in B complement, prove it's in A complement. That is exactly what it means to say that B complement is a subset of A complement. We would be done at that point. Do this. Sometimes in a certain situation, you might just work with the entire set. But always when you see a set containment proof like this, think about going down to the level of elements. Okay, so here's how I would write this. It's going to be pretty quick. Suppose X is in B complement. This kind of set containment here, it's just going to feel like taking symbols here and just explaining what they mean. So if X is in B complement, then X is not in B. You could add a line here saying that every element in A is in B. If you want to, I'm going to assume that comes straight from this hypothesis, the way it's phrased. Consequently, X is not in A. Maybe I'll write here as A is a subset of B. So here's my application of the hypothesis. What does it mean to not be in A? It means that you're in A complement. Pause here. I have one more thing to write. Suppose we take any unspecified element from B complement. Again, sometimes with these starter proofs and set containment, it feels like just taking this and saying, what does that mean in words? To be in B complement means to not be in B. Because of the hypothesis, we can then conclude that X is not in A, because everything in A belongs to B. Therefore, again, I'm just translating what this idea means, kind of rephrasing it differently. We conclude that X is in A complement. Don't stop there. Get to the actual statement. So X is in A complement. Anything in B complement belongs to A complement. Therefore, all right, thus, B complement is a subset of A complement. It's just checking the definition. So it's a direct proof. Whenever you write a direct proof that amounts to showing that a provided definition is satisfied, you want your proof to follow the statement of the definition. So here it's like every element in the left-hand side is an element of the right-hand side. That's exactly the definition of set containment. So that's how we did the proof. Okay, let's do another one. In this exercise, we are going to show that two sets are equal. What does it mean to have two sets equal to each other? Well, we say that A equals B if A is a subset of B and B is a subset of A. This is the marker that I already retired. It's like the thought process that goes into saying that if the number X is less than or equal to Y and the number Y is less than or equal to X, then what has to be true about X and Y here? They have to be the same number. So here it's like if everything in A is contained in B and everything in B is contained in A, then actually they have to be the same set. So that's what we mean when we write down set equality, which means that to show set equality is to show two set containment proofs like what we just did. So what I would like for you to do is pause and do this set containment proof twice to get to set equality. So show that the complement of A complement is a subset of A. And then show that A is a subset of the complement of A complement. So it's like two separate proofs. I will come back in a moment and do that. And then I will show you another way to tackle this that feels a little bit faster. What we are about to do is two proofs that combine to give us the overall statement, just like with an if and only if proof. I think it's polite to the reader to indicate what's going on so that they have a sense of organization when they read through the proof. So we'll start with this direction, showing that the left-hand side is a subset of the right-hand side. That will follow, again, the spirit of the definition. So let X be an element of the complement of a complement. Just like a moment ago, what we're essentially going to do is just take this expression and kind of unpack it, perhaps just kind of rephrasing it differently until we get to the right-hand side. This outermost complement means that X does not belong to the innermost set. Thus, X is not an element of this A complement. But if X is not an element of A complement, then by definition, X is an element of A. Again, these kind of what I would call sort of first few set containment proofs always, to me, just feel like kind of rephrasing statements. It doesn't feel like a very deep conclusion to reach, but there it is. Okay, again, don't stop there. Say what the conclusion for this argument is. So, just keep saying the word so. The complement of a complement is a subset of A. That's what I've established so far by showing that an element of the left-hand side, has to be an element of the right-hand side. On paper, this would go below. On the board, I'm going to do it to the right. Again, just like with an if and only if proof, I like to say kind of the demarcation between the two different arguments that are happening within the proof. Let me also, just to not blur the two arguments together, I'm going to switch to an element called Y. Let Y be an element of the right-hand side. If Y is an element of the set A, then it is not in A complement, because A and A complement are each other's opposites, if you will. Okay, so if Y is in A, then Y is not in A complement. But now viewing this just as a set, to not be in that set means to belong to its complement. Now I have shown that any random element from the right-hand side is an element of the left-hand side. Thus, A is a subset of the complement of a complement. So the left-hand side is a subset of the right-hand side. The right-hand side is a subset of the left-hand side. They must be the same set. That's the only way that could be true. And that's all there is to a set equality proof. I'm going to show you a faster way that you might like better in just a second. But when in doubt, if you are trying to show that two sets are equal, you can split it into two set containment proofs. And then what does it mean to do a set containment proof? Go down to the level of the elements that live inside of the set you want to show as a subset of the other set. Okay, here, notice that these two sets were equal. So I have stuck with my subset notation. But if you were reading a book, it might really want you to do subset or equal, because this is, in fact, not proper containment. This is the only time I'm going to do this, though. I just tried to really emphasize this point that my notation is okay as long as we're consistent with it. Okay, let me step aside, and then I will show you a way to kind of do both of these arguments at once so that you don't feel like you're repeating yourself too much. It's good to know both techniques. I think both give you good tools to use to show set equality. Here's the faster way to do this set equality proof, and let me kind of say what motivates this. A equals B, just thinking about two random sets which happen to be equal. A equals B means X is in A if and only if X is in B. So just like with an if and only if proof, you can show the left-hand side implies the right-hand side and the right-hand side implies the left-hand side. That's what we just did in two pieces. Or just like with an if and only if proof, if you've written a lot of these before, sometimes you can work with both directions at the same time, meaning that you can come up with a chain of implications which imply each other both directions. Let me just do it here. So this is the background idea. Notice I'm going to start here, meaning I'm going to start on the left-hand side, probably overusing the letter A. Notice X belongs to the left-hand side. And then I'm going to do an if and only if chain of implications. If and only if X does not belong to a complement. But this happens if and only if X belongs to A. Okay, it's just two if and only if implications. Whenever you structure a proof like this, you just want to take a moment at the end to make sure that both directions really are valid. So reading this left to right, X is an element of the left-hand side, if and only if X is not an element of a complement, and that happens, sorry, I'm supposed to just go left to right. If X is an element of the complement of a complement, then that means that X is not in a complement, which means that X is an A. Sorry, I corrected myself there because I started doing both directions at the same time, and I really just wanted to go left to right. Let's go right to left. If X is an A, then X is not in a complement, which means that X is in the complement of a complement. So you can see that both directions flow together like this. So if you can construct something like this, it's a fast way to do an if and only if proof, and therefore it's a fast way sometimes to show set equality. So I'm just going to wrap this proof up. I'll write as desired. Not writing very well at the moment, but hence the complement of a complement equals A. All right, let's wrap up this discussion with a proof of something which is fairly substantive, meaning it's a famous result, it has a name. We are going to wrap up our discussion of sets today with one of the statements of De Morgan's law, which we will prove. I'll leave the other one to you to prove as an exercise. This statement involves what's called the set union and the set intersection. I've gone a bit quickly through sets because I think that you've probably seen this before, but if you haven't, let me give you a quick understanding of what both of these sides are saying. If X is in A union B, or the union of A and B, this happens if X is in A or B or both. X just has to belong to one of these two sets. It could belong to both. So this implies X in A or X in B. And that is not a strict or. X is in an intersection. And here I'll write down the intersection that we actually have here on the right-hand side. There we go. If X belongs to both sets. So X is in the intersection of two sets when it belongs to both of them. So what's important here is the distinction between or and. It's a lot easier to belong to a union than an intersection. To belong to a union of sets, you just have to belong to one of them. To belong to an intersection, you need to belong to all of them. Okay, so that's a quick look at set union and set intersection. If I wanted to read De Morgan's law out loud, I could just kind of say what the symbols are telling us. And let me read it left to right symbolically, and then I'll translate it into words, give you a phrase that's a little bit easier to remember. The complement of the union of A and B is equal to the intersection of A complement and B complement. So again, that's just translating these symbols into words. Or how I would read this is the complement of a union is the intersection of the complements. We could actually try to sketch this with a Venn diagram. I don't recommend over-relying on Venn diagrams, but sometimes it's nice just to illustrate a concept. So if I have set A and set B, the union of A and B is like filling in both of these disks. Okay, so A union B, what I've written down here, would be both of these disk regions together. The complement of that is everything outside. So this, what I've done here is the left-hand side of De Morgan's law. So A union B complement looks like this. Let's try to do a Venn diagram now for the right-hand side. And I think I'll make this one a little bit messier. So this is going to be A and this is going to be B. Let me do different colors, orange and blue. I hope you can distinguish these. If I take A complement now and say, what does A complement look like? It looks like, sorry, it's already messy. It looks like everything outside of A. On the other hand, if I take B complement, it's everything outside of B. Probably should draw this the other way. Probably should just not draw this at all. Okay. What lives in both? So, some elements live here, some, including these, some elements live. No, sorry, I shouldn't have done that. Okay, go back to the right picture now. What lives outside of A and outside of B? If you see what's satisfied by both of those conditions at the same time, just to make the picture worse, it is the same as the first picture I drew. Okay, so this is a visual representation of De Morgan's law. Again, the complement of a union is the intersection of the complements. I'm not going to state version 2 for you right now, but it's a very famous result. You can look it up. The second version of De Morgan's law flips the operations here and says that the complement of an intersection is the union of the complements. Very similar statement with a similar proof. So we're just going to prove this version. Okay, let me erase this mess, and then we will come back. This is a set equality proof. So if you'd like to, you can pause and try it, maybe both of the ways that we just looked at. So the first way, you could break it into two arguments and kind of tie them together at the end to get set equality. Or you could try that kind of if and only if, maybe shorthand approach. I'm going to split this into two arguments. You're welcome to roll them into one if you like. To be clear to the reader, I'd like for them to know that I'm going to show that the left-hand side is a subset of the right-hand side. Again, this is set containment that we're about to do. So go down to the level of an element. Let X be in A union B complement, the complement of the union of A and B. Once again, my next step is just to rephrase that. Thus, X is not an element of A union B. We said that you belong to the union of A and B if you belong to A or you belong to B. I'm going to switch into symbolic language for just a second. The negation of two conditions, P or Q, is not P and not Q. Okay, so this is just a logical statement here. So P or Q, not that. So not P or Q is not P and not Q. So to say that X doesn't satisfy the definition of the union of A and B, which can be phrased like condition A or condition B, is to say, I'm just going to keep using the word thus, X is not in A and X is not in B. You might have seen that right away. I just wanted to justify it by looking at kind of a little bit of a logical argument. Let's erase this. Okay, and now I'm going to once again rephrase not being an element in terms of the complement. So this kind of unpacking of the complement versus being an element or not being an element of a set. So just restating the sentence right here. So X is in a complement and X is in B complement. That is literally the definition of X being in the intersection of A complement and B complement. So therefore, X is in the intersection of these two sets, A complement and B complement. Once again, I'd like to see the set statement at the very end. It's tempting to stop here, but I would like to, show that we've actually gotten back to this language. Consequently, this set is a subset of this one. All right, that's one direction. I can fit the other direction on here as well. So going back the other way, Let's start with the right-hand side. And once again, just to keep it clear that these are two separate proofs, I'm going to switch to a letter y from x. Let y be in the right-hand side. I want to just put into words what it means to say that y belongs to this intersection. So y is a member of both of these. Y is in A complement and y is in B complement. And again, I'm just going to rephrase this now by saying that, hey, A complement is the same thing as not being in A. B complement is the same thing as not being in B. Now, the reverse of that logical statement that I wrote down allows us to take, this statement and that statement and flip it into the negation of or. Okay, so that logical thing I wrote down, we're going right to left this time. We find, I'm trying to mix up my language a little bit, that y is not in A or B. How about I write that? But that means that y is not in their union. All right, i.e. y is not in the union of A or B, so y is in the complement of the union. Almost out of room. But I need to say what we've actually shown. Thus, the intersection of the complements is a subset of the complement of the union. We conclude now that these two sets are equal. I'm not going to write that down because I'm going to run out of room. But the last statement of the proof is, therefore, this. Okay, so we showed the left-hand side was a subset of the right-hand side here. Conversely, going the other direction, we showed that the right-hand side is a subset of the left-hand side. If two sets are subsets of each other, they're the same set. Therefore, the complement of a union is the union of their complements. That is one version of De Morgan's law. The other version is the complement of the intersection is the union of the complements. Is a very similar argument, and I will have you work through that on your own. You can also grow De Morgan's law. You could even do it by induction if you're looking at just any finite collection of sets. So if you take A union B union C complement, so that instead of just two sets in here, it's three, you can phrase something analogous over here on the right-hand side, but it doesn't even have to be a finite collection. I don't want to say more there because I really just wanted to get into this idea of showing that two sets are equal. But De Morgan's law has extensions, is what I'm trying to say. Okay, I will wrap this lesson up here. And to make sure that I didn't skip over any set definitions too quickly, after I step away, I will put up a list of just set symbols and terminology and their definitions just to make sure that we really covered all bases for sets in this lecture. In the next lecture, we will actually go to the real number line and we'll talk about its axiomatic structure. It might feel like that should come first because I'm going to use the word axiom in it, but one of our assumptions about the real number line will be phrased in terms of sets. So that's why I wanted to start our discussion of real analysis just by covering sets. Thank you for your attention.